I believe I'm now live. Yep, I'm now live. So yeah, welcome back to today's live work. Well, yeah, we are just we are just actually continuing from the one previously. So yeah, let's actually just jump straight towards it. And yeah, by the way, I have actually been thinking a little bit more. So yeah, I think now I can actually just solve some of these things as well. Oh, like the ones that I just skipped. So yeah, this one here is already correct. And yeah, by the way, when you just actually just plug it in to the thing, right out the and yeah. So basically, why is there no precipitation? It is because of the KSP is actually lower than it is lower than the thing. Because like yeah, when you actually just see this here, I like yeah, I, I just I just write it down as 2.1 times 10 to the power of negative 3, which doesn't make sense. In fact, it literally doesn't make sense at all. So so yeah, in fact this is only 5 times 10 to the power of negative 5, because like yeah, this thing here is actually the maximum here. The x like yeah, that oh 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 like yeah, that is that is the maximum amount. So yeah. So yeah, when you just consider that so yeah, when you just consider that in, that's basically that. Okay. Uh so yeah. Um and by the way, in here inside this 2f minus, there is like this 2.86 times 10 to the power negative 4. And so when you just plug it in, it has not really actually been fully um, t taken out. So like yeah, instead that oh like yeah, instead it has like this 10 to the power of negative 4 inside of it. So yeah. And yeah, by the way, this thing here is started from 2 liters into 3 liters. So yeah, you need to consider that as well. So yeah, basically that yeah, at here you will have like 10 to the power of negative 4 here. And so yeah, basically when you just actually just plug in the numbers in, like yeah, you can oh 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 like yeah, you can actually just ignore the thing, but yeah, for me I don't really ignore it. So yeah, from that 2.86 there, 2.86 times 10 to the power negative 4, which is something that I won't actually write again. You multiply that by 2, add it by 10 to the power negative 4, and no, sorry, let's just let's just write that as 1. You take the entire thing, divide it by 3 liters, which you'll get around 2.24 times 10 to so yeah, this thing here is 2.24 times 10 to the power negative 4. That's that. And so when you just actually just plug the entire thing inside your formula, you should actually get so like yeah, 1.43 times 10 to the power negative 4, and then you multiply that by 2.24 times 10 to the power negative 4. What you'll actually get is 3.2032 times 10 to the power negative 8, which is bigger. Oh wait, no, squared, yeah. I forgot to square the number. So yeah, that thing there should be squared. Squared. That's 7.175168 times 10 to the power negative 12, which is smaller than the thing. Oh wait, the concentration here is actually different. Instead of 1.43 times 10 to the power negative 4, it is actually needed to be it must be re-evaluated again, because like oh wait, that's 3 liters. Wait, oh no, Wait, yeah. Oh no. So I need to reconsider the entire thing. Okay then. So that 1.43, that's 3 liters. 1.43 times 10 to the power of negative 4. That is for 3 liters. And so, to find out how many it is at 4 liters, you just need to multiply that by 3. And then after that, you divide it by 4. So that would be 1.0725, no, 73, 10 to the power of, you know what? 1.08. No, 1.07. 10 to the power of negative 4. And then after that, you just need to calculate the one for the fluorine, which is something that we have actually done. 2.86 multiplied by 3, because that's the amount of liters are there, and then you add it by 10 to the power of negative 4 liters. And yeah, this is just simple addition. You'll get that, and so you'll get 8.5801, which doesn't make sense because that's not what I was supposed to plug in. It's 9.58, and then you divide it all by 4. What you get is 2.3. Let's say 2.4. 2.4 times 10 to the power negative 4. And then for the lead, we just calculated that to be 5 times 10 to the power negative 5 molars. That is for 1 mole. And so yeah. And so when you just put it in, 2.1 times 10 to the power of negative 3, that is for 1 liter. And so if you want to turn it into 4 liters, just divide it by 4. What you'll get is 5.25 times 10 to the power negative 4. 0.25 10 to the power negative 4. There we go. And so after that, you can just go ahead and just evaluate that number. But the concentration is, oh wait, no, sorry. It should be 5 times 10 to the power negative 5. Divided by that is 1.25. 10 to the power negative 5. There we go. And so when you just try to evaluate the things, well, like yeah, for the calcium and fluorine, it does really it doesn't precipitate because of the powers is actually much more bigger. So yeah. And then for the lead fluoride, that would also be very high, and so we can actually just say that yeah, KSP max is less than the KSP we got. There we go. So that's how you actually do that. And so now let's actually solve this one. How many moles of the chemical that you use for part C are necessary to precipitate the original 4.28 times 10 to the power negative 4 moles of CaF2 out of the solution? So yeah, basically this question will literally ask you about the principle of this guy here, CaF2 equilibrium of Ca2 plus with 2F minus assuming that we have here is that the one that, so that yeah, what I want here is 4.28 times 10 to the power negative 4 So yeah, this is ice. So yeah, we want to try to find a way just to make sure that we would get all of this all all of the CAF2 backs. No, so that we can actually just get the CAF2 back. Uh, and so this is the MGF2. Equilibrium, MG2 plus, and then you need 2F minus. We will assume this guy to be X because that's the one that we need to use. And then after that, for this one here, this would be X. This one here would be 2X. That means, because we are just assuming this to be actually fully what do you call it? Fully fully dissociated. So yeah, with that, we can, like, yeah, we can just say that the CAF2 here starts with nothing, but then we got this 4.28, and also this one here. Well, like, yeah, we are now just looking at this from the moles perspective instead of the molarity. So yeah, this times 10 to the power negative 4. So this one here would be 8.56 times 10 to the power negative 4. Okay, okay, and so we add in, oh wait, no, we also add this guy by 2x. Uh, so basically, like, yeah, what we want to do is to get this guy to KSP, which would equal to the concentration of Ca plus, Ca2 plus, and also the F minus. But is it possible for us to actually to make that much thing? Because like when you actually got 0, the KSP would be 0, which would not make sense anymore. So yeah, we need to have something to be increased. Because like how many moles of the chemicals that you use for part C is necessary? But yeah, when you oh oh like when you are actually just solving this problem, oh, you need to consider like lots of these stuff. So yeah, this is a pretty hard question, I should say. The F minus squared. Like yeah, you are asked to be or like yeah, you are asked to actually to release all of those things. So yeah, that is what makes this thing a little bit much more hard to solve. So yeah, 4.28 times 10 to the negative 4 moles of CF2 out. Like yeah, so like yeah, the molarity here is, oh wait, I think I have actually calculated about how many of those are inside the thing. So that's 1.44 times 10 to the power negative 4. Multiply that by 2.86 squared times 10 to the power of negative 8. That's 1.169. Oh wait, Doesn't that actually precipitate? Because we are just using molarity? I think so. Unless my calculation is totally worsening. Worsening. I don't think that's a word. It's 1.169 times 10 to the power negative 11. Which is still smaller. It is still smaller. But not by a lot. So yeah. Uh, so so yeah, in order to precipitate this guy, you want to uh you want to increase this guy because we are just using the chateliers. So yeah, you need to do something. So we want to we want to increase this guy. So this guy would so this guy will decrease. And we want it so that most of these guys will go to here. That's basically the theory that I want. So we started from that 4.28 times 10 to the power negative 4. I don't think we'll have enough calcium to do this. But if we use calcium sulfite, could we do that? I don't like, yeah. Like, yeah, it won't be enough. Because if you even just add in the 2x there, the like yeah, the calcium you have won't be enough, which is the problem. So I would say here it's impossible. It's impossible. Unless if you want to try to do something else, which is to put something else there. Impossible? Like, yeah, according to theory, that's impossible. Oh wait, but we are actually talking about concentration, right? We are talking about concentration, which means that we can actually do this. But we need to make sure that those things should work. And so, in order to release that 4.28 times 10 to the power negative 4 stuff, that's basically 1.43 times 10 to the power negative 4 molars. Which is true. Yeah, it is actually true because, like, yeah, you just divide the top side there by 3. So yeah, 1.43. So like, yeah, you are just basically starting from that initial thing. But yeah, you want to precipitate those original stuffs out, which would be something. So yeah, let's just try to write that down. 4.28 times 10 to the power negative 4. That would be the initial. No, sorry. 1.43. 43 molars of those stuffs, and then you want to get rid of the same amount of calcium fluoride there. But yeah, this thing is actually saying how many chemicals, not the volume. So yeah, we won't care about the volume. So yeah, we will just assume that the volume would be constant, the same 3 liters. So yeah, we need to try to find that out. Okay. When you are actually just doing these problems, I don't know how. Name one chemical. Okay. So we want to try to get that 1.43 times 10 to the power negative 4 molars back. I don't think it's possible. Yeah, because even though that you do all of those stuff, it would actually just yeah. Like yeah, I would say that yeah, it would be impossible to do that because like from what you have that 4.28 times 10 to the power of negative 4 moles of calcium fluoride there couldn't be actually be gathered them all back up. We know that we know that some of them will just stay there, which is the issue. Unless we could actually get rid of all of those 4.28, but that means that we would actually be going literally above the thing. But we are using a bit of theoretical stuff. So we could just assume this guy to be nearing zero, but yes, the fluorine will actually be much more higher. Uh, but then yeah, that would literally mean something else. But what about if you use calcium sulfate? Sulfide. When you use calcium sulfide, the calcium would basically increase, but the amount of fluorine that you have will still be the same, which means that you cannot actually use them all to form those things. So unfortunately, yeah, it is pretty much impossible at this point. Because like yeah, when you just multiply by 3, it's so yeah, unfortunately it is impossible because of the because because of all of those theoretical stuff that I was actually thinking about. So yeah, let's just go back here where we know that this guy here is the number of sites there. Good. And so yeah, let's just go to part B. Well, like yeah, last time we got like 1 hour 45, so yeah, we still have like maybe 1 hour 15 if we are just looking at the time. So yeah, does hydrogen diffuse through the palladium lattice through interstitial or through substitutional? Obviously, this thing will use interstitial because like yeah, when using substitutional, size of atom must be pretty similar. But yeah, we know that palladium is much more bigger than hydrogen. So yeah, that's why. Oh, diffusion, the diffusion coefficient of hydrogen through palladium at 300 Kelvin is 3.2 times 10 to the power of negative 10. You expose one side of the wafer to a hydrogen atmosphere with a concentration of 0.0446 molars and the other to air with a hydrogen coefficient concentration of 2.23 times 10 to the power of negative 8 molars. What is the flux, that's the J, of hydrogen through this palladium crystal at 300 Kelvin? The palladium wafer is 2.7 millimeters thick. Hint, 1 liter is 0.001 meter cubed. Okay, so yeah, the flux here would equal to the D. So yeah, that would be 3.2 times 10 to the power of negative 10 meters squared per second. We need to write all of the units because if you don't, you might end up actually messing the entire calculations. So yeah, that's basically why you actually write all of those things there. Uh, and then after that you got this DC here, which is pretty small. Like yeah, oh like yeah, the air is actually a very small number. It's times 10 to the power of negative 8 compared to the 0.0446. So that's why I would say that 0.0446 molars there divided by the, well, you know what, let's just actually convert this into moles per liter. And then after that we know that 1 liter is 0.001 meter cubed. So yeah, I will just replace that with that, and then you need to divide it by the thing, multiply by 10 to the power of negative 10. That is the change of x, which is 2.7, which is 10 to the power of negative 3 meters. And so you just need to do is to plug the entire numbers in. 3.2 times 10 to the power of negative 10 there. Like yeah, all of the units should match up. Times 0.0446 divided, times 0.0446 molars divided by 0.001 there, and then you divide it by 2.7. No, what just happened? Divided by 2.7 times 10 to the power of negative 3. So when you do this, okay, yep, I see where I made the error. So we should get the number, which should be, yeah. That is 5.26 times 10 to the power of negative 6 moles per meter squared second. So that's that. Good. We have calculated the flux. And so, okay, D. Draw the concentration profile of hydrogen atoms across this crystal at 300 Kelvin. So yeah, basically here, let's just draw the concentration of H, which in this case is pretty high, but then this guy here is a very low one. And then for the wafer, it's just basically the slope here. So yeah, that's basically that. That's the diffusion rate. That's like, yeah, that's the slope. That is the diffusion rate. Okay, at 400 Kelvin, the diffusion coefficient is D. 400 Kelvin equals to 3.51 times 10 to the power negative 5 meters squared. Assume that diffusion follows the Arrhenius law. D equals to D naught times the exponential minus EA over kBT. What is the activation energy of the diffusion of H through palladium? So yeah, the first thing that comes to my attention is that you can actually just compare those two together. So yeah, basically what you can do here, from what I'm saying, is that 3.51 times 10 to the power of negative 5 divided by the D from the previous one, which is, how many was it? 3.2 times 10 to the power of negative 10. 3.2 times 10 to the power of negative 10 must do equal to, the D naught would cross each other out. Instead, you got the exponential of minus EA over kBT of kBT 1. Oh, well, yeah, actually we just actually did number 2 first. T2 plus EA over kBT1. So yeah, that's basically the maths. And so you can actually just take the natural log straight away, or what I'll do is that I'll just actually evaluate the fraction first. 3.2 times 10 to the power of negative 5, no, negative 10. That would be 109,687.4 25, which would equal to the exponential of minus EA over KB KB 400. Well, yeah, actually, yeah, I can. Oh, like, yeah, I can. Oh, you know what? Oh, let me just leave that behind. KBT2 plus EA over KBT1. There we go. And so when you take the natural log of the natural log of the previous one, you'll get 11.61. That's equal to minus. So yeah, it's EA over KB of 1 over T1, which in this case is 300, subtracted by 1 over 400. And so with that, you can just, and so you can take the answer divided by that 1 over 300 subtracted by 1 over 400 there. Yep, that's that. So you got 139.26.47 equals to EA over KB. Oh wait, actually no. No, sorry. So this guy here would be this guy. Multiply that by 1 over 300 subtracted by 1 over 400. I'm so sorry, but yeah, that's that. This would be 9.6711. You know what? That multiplied by 10 to the power of negative 3. So yeah, that's that. And so when you multiply that by KB, I will get the energy in joules, which is something that I don't really like, but oh well. So you take the answer, and then you multiply that by the R, which is 8.314, divided by the divided by 6.02 times 10 to the power of 23. That would equal to this crazy number, 1.36 times 10 to the power of negative 25 equals to EA, which is obviously something that I don't really like. But it is also something that's logically incorrect. Because according to my brain, it should be this big of a number, but oh well. And so we just need to divide the answer by 1.6022 times 10 to the power of minus 19. What? Oh, okay. So let me just do that entire thing again. Take the natural log of the answer, and then you do that crazy thing, and then you take the answer, transform that into that, and then after that you divide that. Yeah, there we go. So what I get is 8.37 times 10 to the power of negative 7. So it's a very small number for the activation energy, which could be why that, yeah. Logically it's correct. Logically. But I don't know. It's 3.51 until that guy, which would be a high number. Yeah. There should be 5 zeros there, which is what I expected. And by the way, that's T2 over T1, and so yeah, using the maths you can actually just do the entire calculation, and then after that you take the natural log of the answer, which is basically basically some sort of the power. So like yeah, from that 109.687.5, you take the natural log, which is 11.61, give or take, and then after that you just multiply it by 1 over 300 minus 1 over 400, just something that I have done. Yep. And then after that, I just multiply that by the KB, which is 8.314 divided by 6.02 times 10 to the power of 23, which gives me that big number, which actually makes sense. And then after that you just use the negative 15, no, negative 19, sorry, which gives you this thing for the EA in electron volts, which is technically true. So yeah, I will say that yeah, that's the correct answer. Good. And then part 2, at what temperature should we hold the palladium that the flux of hydrogen atoms through the filter is 1.38 times 10 to the power of negative 4 moles per meter squared? Second, hint, use the information from part C or part E to determine D naught. Okay, uh, well, 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 it just states or. You know what? Yeah. So yeah, basically what you know is that joule J equals to minus D of dC over dx. There. And so what I can actually do is that I can actually just replace this D here with 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 the literal law of D naught of multiplied by the exponent of minus EA over KBT. Cage them all up there. And so with this you can actually use all of those information to solve this problem. Just by using a little bit of like yeah, a little bit of crossing out, because we don't really need to find out what D naught is. Like yeah, we have found out that 5.26 times 10 to the power of negative 6 is our first answer. So yeah, when you just do the crazy thing that J2 divided by J1 must equal to, well yeah, oh well yeah, the D naught actually crosses out, so what you'll get is the exponential of minus EA over KBT. And then after that, and yeah, by the way, the DC over dx would be a constant, because like we don't actually change any of those, so yeah, we don't need to care about that. So we got that plus the EA of KBT as well, but this one is 1, and then this other side here would be 2. Good, good, good. And so what's J2 divided by J1 is? That's 1.38 times 10 to the power of negative 4 moles per meter squared second, yeah. And then after that, we are going to be dividing it by, let's see, 5.26 times 10 to the power of negative 6. That would give me the answer of 26.24. That would equal to the exponential function of this guy there. Just copy paste that in. There we go. And then we'll just actually take the natural log of the answer there, just to get the answer. 3.27 would equal to EA over KB of 1 over T1 minus 1 over T2. And yeah, by the way, this thing is at electron volts, but yeah, we have already calculated the one for joules, so yeah, we don't really need to convert front or back. as often as before. So yeah, we just need to divide that by 1.36 times 10 to the power of negative 25. We need to cage that in. There we go. 1.36 times 10 to the power of negative 25 electron volts. But then we need to multiply it by the kb. And what is the kb here? The kb is the 8.314 divided by the Na, which is 6.02 times 10 to the power of 23. And so what we will get is 331.77 must equal to 1 over T1 minus 1 over T2. Okay. So in order to, well, yeah, actually, the higher the temperature, the faster it is. The lower the temperature, the lower the D naught is. So that's basically the theory. So that means that we need to have a negative number at the end, which would be a 0 point something number. That's from what my assumption is. Based on all of our things that, yeah, we just found out what the EA is. We know that to be, no, sorry. We know about the joules now. And then after that, we can just use the EA that we got there. So we just use the division law that we got there, which is the EA here is that big number. Wait, actually, we already have the value though. Yeah. So instead, let me just actually use that. So do that, take the natural log of the answer, and then after that, divide it. Yeah, divide it by 9.67 times 10 to the power of negative 3. This should actually give me a better answer. No, never mind, it's still the same thing. Wait, no, it's actually pretty different. When we just use that thing, instead we got an 86 there. Here would be 337. Okay. And so to do this, we need to go ahead and just plug in the numbers. No, so we just need to subtract it by 1 over 300. I know. By the way, this is at Kelvin, so yeah. You got that. And then after that, you want to put the numbers. No, you need to multiply that by negative. What? This doesn't make sense. Which it should be. Okay. Because like I don't really like to actually to find out what the D naught is. The J2 is 1.38 times 4. Well, yeah, the numbers make sense, I guess. Like, yeah, the negative actually crosses each other out. That is something very good. dc over dx is a constant. That, yeah, so yeah, we know that j2 over j1 would equal to that over that. And then that. And then from the d2 over d1, we can actually just cross out the d naught just to get the exponentials only. And then after that, we use the crazy maths to find out that actually that's that. And so that is that. So when you multiply that by that, no, divide it, you'll get a big number, which won't make sense. Like, yeah, T2 would be a crazy small number. That is from what I can tell at this point. T2 is a very big number, as T1 is a small number. What did like yeah what what fraction did I actually use? 1.38 times 10 to the power negative 4, and then with my answer there of J, which is 5.26 times 10 to the power negative 6. So that's J2 over J1. So according to this information, it would be impossible, because the temperature would be negative. Impossible as well. You know what? I need to check this guy again. I don't know. Yeah. To determine the D naught. Yeah, let's just actually go ahead and just figure out what is the D naught. Because somehow that I can actually figure this thing out, which is making me freak out a lot. So yeah, let's actually do that. 1.36 times 10 to the power of negative 25 there, and then you divide it by 8.314 times divided by 6.02 times 10 to the power of 23. Wait, that's EA over KB. Duh. 9.67 there times 10 to the power of negative 3. So we actually get that number. Logically it would be true that the number would be positive. But yeah, logically it should be like a fraction, so yeah. So yeah, we got this guy here, 9.67 times 10 to the power of negative 3, yeah, there we go. And then you divide it by the temperature, which we don't need to care at this point. So when you have this value of, how many was that? 9.67 times 10 to the power of negative 3. What you do is that we need to try to find the temperature. So yeah. Oh wait, no, actually we need to find the D naught first. So when you actually get this number, 9.67 there, we want to divide it by the temperature that we will have there, which is 400 kelvins. So yeah, you'll get 2.4175. And so when you take the power, e to the power of the answer, you'll get a number. Yeah. So yeah, you just divide it by 400 and then you take the power to get that exponential stuff. And then you just need to take care of it using 3.51 times 10 to the power of negative 5 divided by the answer that you got, which will be that, yeah. And here we notice that the D naught equals to 3.51 times 10 to the power of negative 5. So is it possible to actually help this thing lower? The answer is I believe no. Because basically from all of my information there, when you when you actually just do this crazy calculation in, Yeah, that's 10 to the power of negative 3, so yeah. That's 4.46 times 10 to the power of something. Crazy, I know. So like, yeah, that thing there is actually a very small number, in fact. Like, yeah, that's basically just saying, okay, you just need to move that guy by 3. 1, 2, 3. So yeah, it's 44.6. So yeah, 44.6. You then multiply that by that guy, which is also multiplied again by another number. Oh wait, I'm not finished here. Yeah. So this guy here, that's the EA over KB. You you divide by 400, and then you take the negative of the answer. No, sorry. Sorry. So like, yeah, from this guy here divided by negative 400 to get that number, and then after that you take e to the power of that. E to the power of the answer that you got, which would be 0.99999. And so when you multiply that by 3.51 times 10 to the power of negative 5, you divide by the answer that you got, it would be 3.51. Yeah, pretty much similar numbers. That's the D naught. And so when you found the D naught here, wait, so yeah, so yeah, after you found this, you just would get this 1.38 times 10 to the power of negative 4 out. So yeah, you basically just multiply this by the 2.7 times 10 to the power of negative 3 divided by the 44.6. Yeah, just to find out what the D is. And then after that you want to divide it by the 3.51 times 10 to the power of negative 5. Just to get your stuff. And then after that you want to take the natural log of the answer to get that. You multiply that by a negative number. Oh, okay, by negative 1 there. So you get 8.3431. And so that's basically EA over KBT1. We want to divide it by the EA over KB. 9.67 times 10 to the power of 3. And then after that you want to take the inverse over the answer. So yeah, we just basically flip the answer, and that's basically the T. Huh, wait. Well, like, yeah, I think that's the answer. So what I got is 1.159 times 10 to the power of negative 3 Kelvin, which is totally very low. It is very near 0 Kelvin. So yeah, that is basically pretty much frozen at this point. So yeah, it's basically that. Finally, let's go to number 9. 54 minutes. Okay, good. The following diagram shows the pH of some of the most common substances. The strongest acid here is battery acid. The weakest base, you could say it's blood, but yes, yeah, I think blood would be the answer instead of battery acid, which is literally the weakest base ever. But yeah, instead I'll just say blood. And then the neutral substance is pure water. Simple. The okay, the acetic acid ingredient in vinegar is acetic acid. Oh wait, the acidic. So yeah, CH3COOH. You bought a bottle of vinegar and measured the pH of your solution around 2.4, and the molar concentration of acetic acid in vinegar is around 0.85 molars. Write down the acid reaction of acetic acid with water. Label the conjugate acid and base pairs. Okay. So yeah, this is basically some theory stuff. So yeah, CH3COOH plus H2O would would form this CH3 COO minus, and then you will have like this H3O plus. As this guy here is a base, the conjugate base there, CB. This is conjugate acid. This is a base, and this is an acid. No, sorry, this is a conjugate base. This is a conjugate acid. There we go. And so this guy would pair up with this guy, and then this guy would pair up with this guy. There we go. What is hydronium ion concentration of our 0.085 molars of acetic acid? So yeah, you can just basically just take your pH and then just ramp it up. So when you just plug it inside your calculator, it's 10 to the power of negative 2.4. And that's the amount of hydronium ions, which is 3.98 times 10 to the power of negative 3. Okay. And so with this, that's that. Quick one, there we go. Based on the information given and your answer to parts B and C, determine the value of acidic ionization constant Ka for acetic acid. Okay. So yeah, for Ka, we will actually use the same thing. So yeah. So basically, what's the Ka here? The Ka for acetic acid, CH3COH. Oh wait, no, actually that's not how you should do that. Instead, like the H2O is ignored. So let me just remove that guy first. There we go. So this guy would equal to the concentration of CH3 COO minus with H plus H3O plus. There we go. And then divide them all by the concentration of CH3 COOH. With this, you can actually just plug in the entire numbers in, because we know what this guy here is, we know what this guy here is, and then this guy would actually be equal to the other guy because of the balance reaction of those guys. Actually, yeah. No, that's not true. So yeah, in fact, what you'll get is actually this guy here is x squared, and the bottom, and then at the bottom side there is 0.85, I believe. Was it? Let's see. Yeah, 0.85 molars. Oh, there we go. 0.85. Subtract that by the x that you have, because of the reaction. This will give you your Ka, and then we know what the x squared is. So yeah, Let's put in 3.98 times 10 to the power of negative 3. This starting squared. Okay. Let's do that. There we go. Divided by where's the divide? There we go. 0.85 minus 3.98 times 10 to the power of negative 3. That should give me the Ka, which is in here, according to my calculator, it's 1.87 times 10 to the power of negative 5. That's the Ka. Okay, I guess that's that. And so what is the hydronium ion concentration of a 0.01 molar solution of acetic acid? Okay. So from the answer that you have, you want to calculate that, guys. So yeah, basically, for me, I would actually use the I would use the equality to solve this problem. So yeah, the 0.01 molars of solution would be at one point, and then the other side would be the other stuff. So yeah. Let's start with the x squared, which is 1 there. And then for the x there, it's negative 1.87 times 10 to the power of negative 5. There we go. And then for the c, this would be 0.01 times 1.87 times 10 to the power of negative 5, which we would get that. And so when you just enter the numbers, how many are there? That's 9.35. Wait, what? Okay. Something doesn't make sense, I guess. Okay, so yeah, the x squared would be that. Oh, sorry. This thing is 0.0. What? Oh, okay. Never mind, I know. So yeah. First thing first is that you multiply by negative. No, never mind. So it's 1.87 times 10 to the power of negative 5 is the one right over there. And then for the other one there, it's actually negative 1.87 times 10 to the power of negative 7. There we go. So when you just click the enter button, what you get is the real answer. 4.231. 23 times 10 to the power of negative 4. Good. And so we just need to go ahead and just put it into our thing to get the pH. So that guy, take the minus log of the answer. Oh, what? Whoops, wait. And so what you do is that you take the negative log of the answer. That's 3.37. So the pH here is 3.37, which is what the answer is. Good. Finally, number 10. Okay, this is the final problem. Good. And yeah, by the way, I am not checking the answer to be correct or not. Instead, I'm just trying to tell you how you would actually just solve the problem according to myself. But yeah, I am so sorry that I didn't really actually share anything that I was actually thinking about. So yeah, I'm so sorry about that. So yeah, as the universe cooled down after the Big Bang, ionized hydrogen, H plus combined with 3 electrons, E minus to form hydrogen gas. Write a balanced equation for this reaction. Okay. Let's see. H plus an electron would result, no, would result into H. Hey, there we go. To form hydrogen gas. So yeah, you need two of those, and you need two of those. That's simple. When H plus and E minus combine, a photon is emitted as the electron relaxes to the ground state, essentially reversing the process of ionization from the ground state. What is the energy of this electron transition? So this is basically the formula that we started with, which is negative 13.6 by the z squared and then the final minus the initial, which in this case is actually only the final, which is the ground state here, which is 1. And so when you just do the entire calculation, this is also 1. So yeah, the energy is 13.6 electron volts, which is basically the starting point of anything. So yeah, that's basically that. What is the wavelength of the photon that is emitted? So this is basically hc over lambda, because hc over lambda equals to the energy 13.6. And so when you just try to find what the lambda is, it's pretty simple. You just take the h that you have, which is 4.136 times 10 to the power of negative 15. Yeah, yep, and then after that you divide it by the answer that you got. Oh wait, what? No. You multiply that by 3 times 10 to the power of 8, the speed of light that is, and then you divide it by your answer. Wait, what? No. No. You divide by 13.6. There we go. So this would be meaning that the lambda here that we got here is 9.12 times 10 to the power of negative 8 meters. We can learn about the elemental composition of stars by observing which wavelengths are absorbed by the star. Okay? Explain in one sentence why absorption spectra have dark lines as shown in the figure. Known to save money at Copytech, we printed this in grayscale, but it was originally a spectrum going from blue to red. So why is it? Because of the something called the absorption of energy from light energy. So yeah, that's basically the principle. So that yeah, when you basically take in the light in, getting up into a higher state for the electrons. So yeah, so yeah, basically that yeah, those energies, it is being pulled in just to create this higher energy. So yeah. Explain in one sentence why the shorter wavelength dark lines are closer together than the longer wavelength dark lines. So yeah, it is because of the energy of orbitals, which basically goes in 1 over n squared. Energy of orbitals, like yeah. Oh, like yeah, basically the 1 over n squared is basically where it is all from. So, also like yeah, basically from the formula. From the from the energy formula. Basically that's how I actually see that anyways. And then Okay, we got Professor Grossman. Let's see. Okay, okay. Wow. So yeah, this is a modified image of astronaut waving. Original source unknown. All right reserved. This content is excluded from our Creative Commons license for information. See HTTPS OCW MIT EDU fair use. Well, yeah, that's Professor Grossman, and yeah, it is the end of the final exam. You are 3.09 done. Was it 3.09 fun? As for us, we will miss you a 3.09 ton. Okay? So yeah, that's basically 3.091. I so yeah, I have finally finished 3.091, which gets me excited, but yeah, obviously there's like lots of things that I don't really understand, especially in those mixing. But yeah. Oh, but yeah, with all of that, I guess that's it for today's live work. So yeah, so yeah, oh, thank you very much for watching the stream, and yeah, we will later actually have like some other things to be discussed according to MIT OCW. So yeah, thank you very much, and we'll actually see you guys later. Goodbye.